Well, thank you for being here. It's a great pleasure to be here to talk about something that's pretty exciting. In fact, it's a bit of a surprise for myself because I'm one of those guys constantly on the other side of the picket line complaining endlessly that Java sucks. And for me to be here to talk about the praises of Java, and I think it deserves every bit of it, is pretty surprising. If you really look at Java itself, what really happened in Java over the past 20 years? When Java was released, yeah, definitely exciting. Java 1.1 had some really nice features. And then what happened? Well, Java 5 eventually had some features which are pretty questionable. I don't think anybody gets too excited about out-of-boxing and things like that. And then nothing really happened again, and Java 7 had some really fantastic features. You could put underscore in numbers. This is awesome because as I'm getting older, that's a feature I'm really beginning to use a lot. Well, nothing really happened. Well, all that changed in Java 8, and Java 8 is probably the most resoundingly powerful release of Java. I can't even imagine anything as significant that's happened in Java as it has been in Java 8. Well, where did that really come from? If you really look at the evolution of Java, Java has really introduced a feature that is rather relatively old, but certainly something that is very powerful. And it's been well tested and used in other languages, and finally Java has adopted to it, and that comes from Lambda Expressions. So we talked about how Java has evolved, but for what reason, what's the purpose of it? That's what I want to talk about here today. Well, best time to ask questions or make comments is when you have it, so please don't wait till the end. Anytime is a great time for questions, comments, anything you want to share, don't hesitate at all. So let's talk about what's really happened here. Well, let's get back to looking at one very simple, common example I'm sure we all have done at various times. So I'm going to say new thread here, create a little thread object. I'm going to say thread.start, and then as soon as I start this thread, I want to also go ahead and say, for example, let's say in main over here. Well, obviously this is going to say in main, but I want to do something in this other thread. So what do? I'm going to say new runnable over here. And then of course I want to implement that runnable, so I'll say public void run. And then of course within this I'm going to say in another thread. Well, if I run this code, of course, you can see that it said in another thread. Well, this is something we all have seen 1,000 times, right? But if you really look at it, can anybody tell me what this is called? When you say new of an interface?
Anonymous class?
Well, you call it anonymous inner class, I call it missed opportunity. Because way back when they were introducing anonymous inner class, I remember clearly that day taking a marker and saying, this author doesn't understand Java syntax. And about the 4th page I said, wait a minute, this author cannot be this wrong. And that's how I learned about this new concept called anonymous inner classes. Well, rather than introducing anonymous inner classes, they should really have introduced Lambda expressions way back then. Why is that? If you really think about it, if you were to explain to somebody what you are doing here, what would you be explaining? You would be saying, well, we want to run a little piece of code in another thread. That's what we're really doing. Well, that piece of code you want to run in another thread is that one little line of code. But what we told this one little line of code is we said, this code came to us one day and said, can I go to the neighborhood park, please? And he said, no, sweetie, you cannot go alone. You need adult supervision, right? So we wrap this into an object, and then we send this object over. How sad that really is if you think about it, right? And this little function has been crying for about 15, 20 years now, right? Can I go alone, please? No, you cannot go alone. Sorry, we got to send an adult with you, right? Well, Lambda expressions are really anonymous functions, and we get to treat functions as first-class citizens. We give the respect the functions deserve. So what we are saying here is, if you really look at this code, if you highlight this part, there's only one name for this highlighted part. It's called the ceremony, right? We're creating a ceremony around this and saying, I'm going to create an object, I'm going to create a function in the object, and then I'm going to put the code in it. Let's get rid of the ceremony completely. And then of course, this is the body of the code separating the parameter I'm passing in, and then the remaining part of the ceremony, right? Ceremony never comes alone. So right there is the remaining part of the ceremony. We get rid of it, and the code still works. So the point really is, we don't need to wrap the function in an object. We can treat the function as a first-class citizen. So a lambda expression is really an anonymous function. So it is a function, all right. So if you really look at functions, most of the time we would say functions have 4 things to it. A function has a name, it's got a parameter list, it's got a return type, and it's got a body. Well, of the 4 things, the name, the return type, the parameter list, and the body, what do you think is the most important? The body of the function. Without it, nothing exists. So right there is the body of the function. That's exactly what we are looking at. So just the essence. Well, of course, the parameter list is important as well. So here is the parameter list. In this case, it's an empty parameter list. Hey, what about the return type? Oh, we can figure out what the return type is. We don't have to specify that. What about the name of this function? Who cares when everything is done? What the name is, it's anonymous. So in other words, we are creating an anonymous function and simply passing an anonymous function to the thread. Now, there are a couple of very interesting things going on here. One is we are able to pass an anonymous function. That's pretty exciting. But also notice, we took what is a good 20-year-old class and we are passing an anonymous function to it. And I think that is one of the things that I really feel is awesome when it comes to Java. You see, when it comes to backward compatibility, the world has shown us one thing. If you don't support backward compatibility, you are doomed. And if you support backward compatibility, you are doomed. So the point is, you're going to be doomed either way. So the question is, which way do you prefer to be doomed? And C# chose one way, right? They're not going to be backward compatible. Well, Java went the other way. Java said, we're going to bend over our back to support backward compatibility. So when it comes to lambda expressions, they didn't create lambdas and say, good luck with it. Now you can either use lambdas or go home. Instead, they made it extremely backward compatible, and that's not an easy task to do, where you can take something that's 20 years old and suddenly send a lambda expression to it and the code just works. And so that is one of the things that we should really kind of read between the lines, if you will, and I think that's pretty remarkable in the way that they have designed it. So a lot of times people look at this and say, they complain, oh, I don't really like this, but there is rationale behind a certain design. And if you really look at all these design constraints put together, there's a reason why things come together in a certain way, and that backward compatibility has been provided in this particular case. So with that said, the next question is, how does this really work? Well, you just saw this a minute ago. I took what was an anonymous inner class and simply replaced it with a lambda expression. So we could naively say, oh, so anywhere a lambda expression is used, it could be used in place of an anonymous inner class. Well, that's true. Well, if that is really true, let's think about this a little bit further. Let's say for a minute I have a list of numbers over here, and say, let's say values equals, and let's say arrays.asList. Let's come up with a little list of numbers here, if you will. So I have this list and I want to iterate and loop through and print all these values. So we could say int I equal to 0, and then I could say I less than values dot, is it length? Size. Are you sure it's size?
Yeah.
Not length, not count. Okay, I trust you. Size, is it plus plus?
Yeah.
Okay, all right, it is. All right. Oh, wait, is it less than or equal to?
Less than.
Most of the time, but sometimes it's not. When is it less than or equal to? When you have this off by 1 error. How does that feel? Right? So the point is, what are we trying to do here? Loop and print the value. And what effort does it take to do that? So if you're into design patterns, I got a name for this pattern. This is called self-inflicted wound pattern, right? We take a lot of effort to do this darnest of simple things, and then of course we're not done yet, right? And then we say output, and then how do we output this? Values.get, of course, to add insult to injury, right? So now we can run this, and yeah, there's the result. But why go through all that effort? We can do this in a lot easier way. We could simply say values.forEach, and then we could say, given a value, simply print the value. There comes the anonymous function again, and we could use internal iterators. So in this particular example, but what are we really doing? Let's take this and dissect this just a little bit. Rather than calling this, I'm going to say values.forEach, and I'm going to pass to this an anonymous inner class, consumer, and I'm going to say integer, And then I'm going to pass to this a public void accept, which is going to take an integer value, let's say value. And then within this, I'm going to go ahead and print out whatever that value is. So if you look at this code, it doesn't know what consumer is. We can help with that. So I'm going to say function.consumer, which is where it's coming from. And you can see the internal iterator work. But you can see how noisy this really is because we're using an anonymous inner class, which is called the consumer. What in the world is consumer? Well, Java calls these kinds of interfaces as functional interfaces. And every time I use this word functional interface, I just laugh because if there are some interfaces which are functional, what about the other ones? Are they dysfunctional? Anyways, right? So the point really is that these are functional interfaces. Well, let's think about this for a minute. If all that the compiler did, let's assume so, if all that the compiler did was simply replace a lambda expression with an anonymous inner class. Let's just entertain that thought for a minute. Now what's going to happen if that was the way it implemented it? Well, let's look at something else real quick. I'm going to go back here and say sample over here, which is where I have the files. And I'm going to say sample, and did you notice there is a sample and then there's a sample $1. There are two files sitting on the disk. Let's go back to the code for a minute. If lambda expressions were so sweet and so easy to write, you're not going to write one of them. You're going to write 100 of them, won't you? And if you're going to write 100 of them, and if the compiler simply replaced each one of the lambda expressions with anonymous inner classes, guess what's going to happen? Well, when you go look through the code after all, when you're trying to look through, let me make sure I put it in the right place. So if you're going to have all these lambda expressions simply replaced as an anonymous inner class, then what's going to happen? Well, it turns out what would happen in that case is when you look for the sample, you're going to look at something very terrifying. Now, can you imagine if every lambda expression is converted into an anonymous inner class? Well, that's exactly what a lot of languages on the JVM actually do. What does Scala do? What does Groovy do? Well, they all do this. Well, then why can't Java do this? Well, there's one difference. When 9 million people use your language and 1 million of them know where you live, you have to make very different decisions, right? So imagine you have an enterprise application and suddenly you say, welcome to Java 8, now your jar file is that big. You're not going to invite friends doing that. And imagine how long it's going to take to load up your jar file when you have that many classes to load. That only makes things worse. You're going to have more load time, more time to move around things. The JVM gets bloated, more memory usage, concurrency issues that come out of it. This net sum is going to be a lot negative. So they said, no, we can't do this. So what do we do? How do we solve this problem? Well, this is where life has some really interesting surprises. Well, forget this for a second, we'll come back to it. Well, Java guys were working on Java 7, and as they were working on Java 7, they did something what I call as a true act of kindness. There's no other word to describe this. They looked around and they said, look at these brothers who program in these dynamically typed languages. Misguided, nevertheless, but they are programming in these languages, right? And what if we take a little pity on them? What if we provide a feature that will make their lives a little better? And so they decided to provide a feature called Invoke Dynamic. Now the word Invoke Dynamic actually, as you see, has two words in it. There's invoke and then there's the word dynamic. So Invoke Dynamic is nothing but late binding, late as in push it all the way down to the bytecode and the JIT level. So think of Invoke Dynamic as true polymorphism at the bytecode level. So literally what Invoke Dynamic does is, it says, I'm going to bind to this function at the runtime, at the JIT compile time, and I'm going to kind of forego type verification just a little bit. It turns out the most statically typed language out there is the bytecode. And it's not the Java that's statically typed as much as the bytecode which is statically typed. There's only 4 invoke instructions in earlier versions of Java. Those are invoke virtual, invoke private, invoke static, and of course there's invoke interface. Well, all these 4 invoke methods are very much statically typed. It'll come and ask you who you are, what's your address, what are you trying to talk to, do you have permission, rejected if you don't qualify any of these. So Invoke Dynamic says, oh, just look the other way. Why? Because you all will agree it's more fun to get errors during runtime than compile times, right? So it says, I'm going to just discard this for now. I'm not going to worry about it. So it literally says, I'm going to bind to this particular call at runtime. And so they created this entirely to support dynamically typed languages. That's what Java 7 did. Well, once they released Java 7, they were sitting and scratching their head about the problem we just talked about. And they said, what are we going to do? And I'm sure that when this guy said this, everybody said, you are crazy. Because what they decided was, why not use Invoke Dynamic? That was the craziest of ideas ever, in my opinion. So once they realized they could use Invoke Dynamic, all of a sudden, the language that uses Invoke Dynamic the most is not Groovy or JRuby or other dynamic languages. It ended up being Java. This I call as the story of good karma, right? You always do good things to others, it pays you back really well. So eventually it became the most powerful feature for Java language. So if you notice over here, I'm going to go back and say, do the same operation like we did, but I'm going to replace that several times over, as you can see here. But now I go back here and say classes and let's say sample, and look at the quietness in there. There are no anonymous inner classes, period. Hey, what just happened? How did that work actually? So Java P minus C minus private, I've already configured that to say that. And I'm going to look for the sample. Let's take a look at what we have here. And this is a peek at the bytecode, and guess what we see here? I look for Invoke Dynamic, and sure enough, there it is. So every one of those calls became a call to Invoke Dynamic. So Invoke Dynamic has multiple different advantages. One, there's no bloating of bytecode. In fact, the bytecode is smaller than it was before with the anonymous inner classes. That's one big benefit you see. The second benefit you see here is, if you never really invoke this method, there's no binding that happens. So the binding happens, you pay the price the first time you call, much like calling a virtual function, but it's a JIT optimization anyways. And also it determines what to call, and here's the beauty of Invoke Dynamic. It doesn't care who you are, it cares only about your signature. It doesn't care what class you belong to. It doesn't care what your name is. All it cares about is, do you have the parameter types that I expect in the order I expected? It's a signature that it really matters. So Invoke Dynamic directly binds to any function as long as that function has the signature that is expected. So that's pretty dynamic in that regard. That's where the dynamic behavior actually comes in. So that's basically how that's being implemented under the hood for all practical purposes. So I'm going to show you quite a number of other things, but as you saw already, I don't use any slides here, but if you're interested in looking at the code example I'm showing you here, you can download from the downloads link up there. You can also download it, the same link in the bottom. You don't have to rush to write it down. As I scroll through, it'll appear again in the bottom as well. So let's talk about where does this take us? Well, to me, functional programming has some really interesting key ideas, and these are the ideas that's been brought over to Java. But let's talk about this for a real, a quick second. Don't worry about being wrong. I'm wrong most of the time, or my wife says me so. So don't worry about being wrong. But can you guess what year object-oriented programming became mainstream? Like everybody did OO without thinking. What year was that?
1994.
94. I'll give you that maybe a couple of years before or after. 5 years this way, that way. Yeah, 1990s. Great. What year was OOP created? 1967. Can you imagine that? 1967 to 1990. If OOP was a human, it had a terrible childhood, neglected childhood, right? Nobody cared about it until it was 23. Hey, handsome, right? So what a long time before that happened. Well, here's another question. What year did functional programming became mainstream? Okay, that was a trick question. It has not yet. Okay, what year do you think functional programming was introduced?
68.
68.
1930.
1929. 1929. Everybody here knows Alan Turing, right? This was Alan Turing's professor, Alonzo Church. In 1929, they introduced a lambda calculus. Now think about this, 1929. And we are still getting excited about it. When people come to me and say, in computer science, everything changes very fast, I look at them and ask them, what are you smoking? Right? It's taken 80 years and we still haven't gotten it yet, right? So I don't think things really change that fast as we would like the world to believe, right? But it's taken that long, but why? Well, they were way ahead of their times. They created stuff that actually solved problems we never actually faced until right about now, we're beginning to face the problem. And one of the key ingredients of functional programming is immutability. Now think about mutability for a minute. You go ask around people and say, what do you think of mutability? And every Java programmer would say, well, it's okay, right? Why? Because everybody does it, right? So we all do mutability. How could we say it's bad? So mutability is okay. What about sharing? Sharing is a good thing, you would agree, right? Because remember what mom tells us. Mom says sharing is good, share, share. So sharing is good, mutability is okay, but shared mutability is devil's work. And the minute you bring in shared mutability, all kinds of things go really bad in systems. Well, functional programming at the very root honors immutability. We don't mutate anything, period. Well, you may wonder, wait a minute, if you never mutate anything, how in the world can you possibly write any meaningful system where nothing changes? Actually, I can show you one application where it's absolutely immutable. It's pretty incredible. Nothing ever changes. And that one actually starts with the main and ends with nothing in it. Right? See, that's immutable, right? But it doesn't do a whole lot either, right? Well, so how in the world can you ever create something that is absolutely immutable? Well, the guys who work on functional programming are extremely smart. You go to them and ask them this question, and they will throw the answer at you called monads, because nobody understands what monads is. That's really cool, right? So to me, a monad is kind of like the Las Vegas model. What happens in Vegas stays in Vegas, right? So the point is, what is otherwise a bad thing to do is kind of done in a very controlled manner. So mutability is really bad. Why? Because it introduces side effect. But monads introduce a sequence through the code that is otherwise not being implemented. It's pretty fascinating when you look at languages like Haskell, because every single statement in Haskell can run in any order, unimaginable when you look at code like Java, but you can pretty much say here's 5 statements. The 5 expressions could run in any order. You have no clue. Most of them it may not even run, because it's if nobody uses the result, why bother running it? So the point really is, it is extremely efficient and built that way, but we have been programming in imperative languages for a long time. It's really hard to imagine how you could even program meaningfully in that area. But we can, and we will do some of that today, how we can get to this immutability. The second thing that functional programming provides is this called higher order functions. Well, higher order functions simply means that you can do with functions what you've been doing with objects. You can create objects within functions. Now you can create functions within functions. You have been passing objects to functions. You can pass functions to functions. You've been returning objects from functions. You can return functions from functions. So in other words, functions become first-class citizens, and we can treat them and we can decompose applications with them. So we've been doing object composition and object decomposition for a while. Now we can intermix that with function composition and function decomposition as well. So your building blocks are no longer objects. You could decide whether you want to be more object-oriented or more functional, or you could combine them, if you will, in languages like Java. Well, then comes the next charm. You deal with what are called function composition. Now, this is one of the most fundamental differences is, in Java, at least the way we started programming in Java, we started really doing state mutation, which is pretty sad if you really think about it, right? We take an object, you poke at it, it changes the state, you poke at it again, it changes the state, and then we tell ourselves, don't do that too much because it cannot handle multiple calls coming in. Then we start putting structures to protect that state change. What if we don't do state mutation? What if we start doing state transformation? For example, let's say I have a $10 bill and I'm going to ask Steve to make a change for a $10 bill, and I ask him, Steve, could you break it? And if he happily gets up and tears it apart, I'm not going to be really that happy. Look at the smile he has on his face, right? He's got every intention to do this. But what I really expect is the $10 to disappear in his pocket and two $5 to emerge, right? That's a transformation, not a mutation. That dollar bill did not get mutated, but we got a new set of dollar bills coming out. So what if we model a system where we have transformations rather than mutation? I know what you're thinking. You're thinking, oh gosh, this sounds really nice, but what about performance? Well, what if the performance is not an issue? What if the languages can handle that in a very efficient way so we don't have to really worry about it? It changes the way we think. So we go through a series of transformations rather than mutations. Then comes along what is called lazy evaluation. This is one of the most charming features, and we're going to see how that actually plays a role as well. To me, these are the key ingredients in functional programming. But let's start with the very first one, honoring immutability. How in the world could we do anything without mutating stuff? It seems like an unbelievable idea. So let's look at one example here as to how we can do this. So let's say for a minute we are interested in taking values in a collection. So let's say we have a list of integer, and then we'll call it values equals new. Let's say arrays dot as list. Keep it extremely simple. These are the values that I want to work with. Now the problem given to us is I want to double each of the values in this list and create a new list. I'm sure everybody in this room has done it a million times over, right? So what is the first thing you're going to do? You're going to say list integer doubled equals new array list, and you're going to create one object, which is the destination object. And then what are you going to do? For int I equal to, okay, let's not go through that again. We will simply say values here, and then I'm going to say doubled dot add e times 2, and then when we are done with this, we're going to say doubled over here, right? So right there, we have doubled each of the values. Anybody here who has written code like this before? Absolutely, right? Some brave ones raising their hands. Others are wiser not to ever raise their hand for that question. Agreed completely. But the question is not if you have done it. The question is, how do you feel when you write code like this?
Dirty.
Dirty, right? That's the way you feel, right? You go home in the night, the children come running towards you and say, don't touch me, right? I gotta go take a shower, right? Why? Because this is called primitive obsession. We said, no, Java, you cannot handle it. I gotta tell you every step of the detail, right? So we come down to saying very, very single step. First, create an array which is empty. And if you're a human doing this, you'll get angry, right? It's like, what do you want? Tell me. Why do you keep telling me all these single steps to do? Well, that is what we did. Then what did we do? Look at line number 9. What is happening on line number 9? Mutation, isn't it? If I turn up the volume of the computer and run this code, you would literally hear the collection double say, ouch, 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 on that line of code, right? Because you're poking at it so many times. It's like, why can't you just give me the values and go home? Why do you keep inserting one at a time, right? So this is a very low-level code, as you can see again. Well, that is an example of an imperative style of code. There are two smells to imperative code. One, it feels like you're talking to a toddler, right? Sweetie, be careful, stand up quietly, don't look anywhere else, walk slowly, hold it with both hands, please. And you got to give every single instruction to the toddler. That's how it feels. You got to manage every single step. Second, you're mutating the code values so many times. Let's try this again. This is a declarative style, and what I'm going to do in the declarative style, I'm going to simply say values.stream. Hey, what in the world is a stream? Think of a stream as a very fancy iterator. We know iterators in Java, but what do iterators do in Java in the past? They give you an element and tell you if there are more elements. That's a go home, right? Well, this is a very fancy iterator. It can do a lot of stuff for you. And so what I'm going to do with this is I'm going to say map to int, given an element, element times 2, and I'm going to collect that result to a list when I'm done and put that back into a list and return it. Well, that collect method comes from, let's go ahead and say a static import over here. And that comes from a stream.collectors. And that's where I'm going to pull that from, and that's the to list coming from. So I'm going to run this little code, and we are using what is called a collect method to pull the data back over here. Actually, in this case, a map is good enough for us. So notice in this particular case, we got exactly the same result, but look at the code in the bottom compared to the code in the top. The code in the top, I'm sure people have told you this, they call that a simple for loop. But they got this word completely mixed up. That's not the word simple they're looking for. That's a word called familiar for loop. There's a very big difference between simple and familiar. Like my in-laws, very familiar, but definitely not simple, right? So the point really is, you don't say that's a simple for loop, it's a very familiar loop. So many times I've looked at it, don't want to look at it again. But if you really think about it, there's quite a bit of complexity built into it. You have to manage every single step of the things. This is somewhat unfamiliar to us, but relatively simple. Why? Well, Michael Feathers tweeted this once, and I thought this was a brilliant way to think about it. He tweeted that object-oriented programming, we encapsulate the moving parts. In functional programming, we eliminate the moving parts. So you're removing the moving parts rather than trying to encapsulate the moving parts. Why? Because moving parts is what keeps us at work in the night, right? We're trying to debug the code because the moving parts failed at some point. So the point really is, you take a collection of values and you perform a map operation. What's a map operation? A map is a transformation operation. Given a set of values, you are applying the transformation on each one of the values, a very high level of abstraction. You're not sitting there and babysitting and saying, do this for this element, then the next one, next element. Instead, you're saying, apply this, and that's the word in functional programming, the word called apply. So apply this function, this anonymous function, on every element and give me a resulting collection. And once we get a collection, that collection itself is a stream, and we are then tying it down, grounding it down to a specific list implementation in this case, and we performed a transformation operation. So as a result, we can focus on more higher level of abstraction. So a very key distinction here, we notice this code in the bottom for a minute. If you notice in this code, not only it's more declarative, it's easier to express, but this code here, we did not torture any variable in the creation of the result. This is very humane code if you really think about it, right? Whereas this poor double got so injured, right? Whereas here, we didn't really torture any variables. It is nice humane code. So that's first one thing is, we don't mutate anything. We honored immutability by going into a declarative style. The other benefit that you see in this case is a very easy to express code. You are able to say what you want and not have to say how to actually do it. And we get drained. Imagine you have to be with a toddler 24 hours a day. No matter how cute the toddler is. After a few hours of time, what do you say? I want to go talk to an adult, right? You don't feel like you want to sit there anymore. That's how the code, imperative code begins to feel. You're just at a very low level of coding. Whereas here, you're very expressive. You say what you want, and the code is able to get this done for you. Well, that brings the question. I keep using the word declarative. What's the relationship? Well, the relationship is every single functional code is declarative, but not all declarative code is functional. So declarative simply means you convey your intent and it figures out the rest of the details. You could write declarative code in almost any style of programming. Even in Java, if I give you a collection and I ask you to go find if Steve is in the collection, here's the imperative way to write this code. For every name in the collection, take one name compared to Steve. That's imperative style. Or you could simply say collection.contains Steve, no looping, and the looping is under the hood, under the contains method. That's declarative coding, nothing to do with functional programming, right? So declarative is simply very communicative, expressive. But you can be declarative, and functional programming is right inside of declarative. All functional code is declarative, but not all declarative code is actually functional. So one of the key parts of functional programming is we're using all these constructs together and being very declarative in what we do. Well, that's great so far, but I want to really look at the higher order functions. That's the second thing I talked about, right? We got the immutability part taken care. What about declarative? That's great, but what about higher order functions? Let's look at one other function that I want to write over here and see how it feels in here. So let's say we have a collection of values. So let's say for int I equal to 1, I less than, let's say, 10i plus plus. And I want to say here, just a question for these, each of these numbers. Output, let's say printf over here, and let's say a %d, and then I'm going to say a %b, and let's say in this case the value I, and e is prime the value of I. So that's all I'm going to ask for just now. So let's go ahead and implement this function here real quick. So let's say we have a static boolean, is prime, and this takes a number, let's say int number. And what do I want to do? Let's start with returning false so I can make sure the code so far is working. So I want to know if a number is prime or not. How would we do this? I'm sure everybody here has done this at some point, right? So you say if number is greater than 1, because 1 is not considered to be a prime number. And then what do? You would say for int I equal to 2, I less than number, without worrying about so much about efficiency of this call. And then we would say if the number mod I is equal to 0, then I want to say return false because it's no longer prime. Otherwise you say return true. So in this case, of course, you run it. It tells you 1 is not prime, 2 and 3 are, 4 is not prime, 5, hey, seems like it's working, right? An ugly way to make sure that things are actually doing something. But if you really look at this code, what's happening in this code? Notice the primitive abstraction again, low level of coding. And if you look at this code and somebody says, what does this code do? Normally the answer is, I'm trying to figure that out, be quiet, right? So we're trying to really read through every single line of code. It's not very expressive. Let's try this one more time. I'm going to go ahead and bring in this case, a stream.int stream. So once I bring in an int stream, notice what I'm going to do here. I'm going to get rid of all this garbage here that we just saw. And instead of all this extra work, let's try to redo this a little bit more declaratively. So return, how powerful that is, right? Return what? Well, first of all, number is greater than 1 and I'm going to say int stream.range, and I'm going to start with the 2 and n1 before the number, and I'm going to say dot, and I'm going to ask him none match. And what do I want to match here? Given an index, let's call it I want to say number over here, so the number given number, mod I is equal to 0. So of course I can refactor this a little bit more if I want to, but look at the expressiveness of this code. You are saying the number is greater than 1 and none matches this property, this predicate, and so the code becomes extremely expressive, and you're not dancing around doing low-level stuff. You're letting the code iterate through and do its job, and very highly expressive, as you can see. You probably saw another pattern emerging over here. If you notice how I've been lining up all these dots. Isn't that beautiful? You get to line up these dots. That is the function composition we are talking about. But what is the higher order function here? Well, none match is a higher order function. So why is none match a higher order function? Because to the none match function, as a parameter, we are passing another function. So that highlighted part is the anonymous function that we are passing to none match, and that makes none match a higher order function, because the higher order function says, I don't really insist on you giving me an object. I'm more than happy to work with you if you give me a function as well, and so that becomes very highly expressive. So that is an example of how you can use higher order function. So what does that mean? As we start programming in Java, we're going to start thinking about programming in very different ways. So you're going to still accomplish the same things you did before, but you're going to do it very differently. And this is the biggest challenge, right? I'm sure you have some people at work who have become Java programmers and they have retired while they still come to work, right? Because they know every single API and they can code in their dreams. They wake up tomorrow morning, and with Java 8 on the job, everything around them has changed. These people are going to be very angry, so stay away from them, right? Because everything they once knew is no longer valid. So I'm going to say the biggest change in Java is not Lambda expression. The biggest change in Java is going to be in the minds of the programmers. Because we have to reprogram ourselves and start thinking more declaratively because we are so used to thinking in imperative style, and that is where the biggest challenge is. The compiler is not going to come and tell you that this is not the right way to do. There are some IDEs like IntelliJ IDEA, for example, will give you a little light bulb and you click on it, it'll swallow your imperative code and then spit a declarative code on you. But still you got to put some effort to really transform the code and start writing it in more declarative style. That's where the biggest challenge is. But having said this, okay, we have used a higher order function, but how do we create a higher order function? Well, this is one of the biggest distinctions in Java compared to languages like Ruby or Scala, because in those languages you could declare closures or Lambda expressions very differently, but it's not that trivial to do in Java. And the reason for a little bit more effort in Java is, remember the backward compatibility I talked about. Because they want to be able to pass Lambda expressions to previously written code. So as a result, Lambda expressions always hide behind a functional interface. So either you have to create your own functional interface, or you got to use one of the predefined functional interfaces given in Java util functional package. So let's look at an example of using a Lambda expression here in our own code. In other words, how do we create our own higher order functions? So to do this, I'm going to come up with a different example here. So let's hypothetically say that you are at work on a Friday night, and you got a very important party to go to. You're all excited about people you're going to see. And as fate may have it, one of your colleagues, you know, the one I'm talking about who nags you all the time, says, I want a function from you. All right, I'll write the function, but I got to go really quickly. What do you want? Well, imagine we have a bunch of values, your colleague says, and I got these values, let's say these values 1 to whatever the values are, and your colleague says, I want a function to total the values. That's it? Absolutely, that's all I want, you say. Well, he says, right? So what do? So you say public static int, let's call it total values, and that takes a list of integer, let's call it numbers. And what am I going to do within this code? Well, all I'm going to do within this code is, let's say result equal to 0 for a minute. Return the result when you are done, of course, right? That's the end point of what we want to get to. But what do you do within this function? So you say for, in this case, and you're going to say int element in numbers, and then you're going to simply say result plus equal to element. That was pretty easy, wasn't it? So that's totaling the numbers, very low level primitive obsession, but hey, it works. So you get that done, and you're done, you're about to pack up your stuff and go to this wonderful event that you want to go to, but your colleague comes over to you and says, I need one more function from you. What do you want? And your colleague says, I don't want to total only the values, I sure want that also, but I want to total only even values. You say, wait a minute, you want something like total even values like this? And your colleague says, yep, that's exactly what I want. Can I have it now, please? Well, you look at your watch, it's getting very late. You look at your code, and there's some good news in the code. Almost everything is done, almost everything. And you tell yourselves, looking at your watch, there's got to be a reason why they created copy and paste, right? I mean, if nobody should ever use it, would they ever create it? And in fact, it's so cool, they even have wonderful shortcut keys, Control-C, Control-V, how cool that is, right? So you change it to total even values real quick, and you say if E mod 2 is equal to 0, then total not otherwise, how cool that is. But as soon as you finish it, now that you're doing really good, your colleague comes to you and says, but please, I need one more function from you. I want to total all odd values. Now you clearly know that copying and pasting a code a third time is an act of criminal negligence, right? But it's Friday evening and nobody is looking, right? So you copy and paste it one more time and you get that working really quickly, and that becomes total odd values. And then of course you say not equal to, how cool that is. Now of course you say, how dare would you check this in? No, you wouldn't. You use your colleague's user ID and check it in, right? So what it really is, you get get that through, right? But you're on the way and guilt eventually kicks in. You know you didn't sign up for this. So you pull up by the nearest Starbucks, you're trying to refactor this. As fate may have it, some of your friends are hanging out there. They come to ask you what you're doing, and before you can shut your laptop, they look at your code and they get to know your dark side, right? They don't return your phone calls anymore. How life changes, right? Because who wants to hang out with people copying and pasting code for a living? Well, let's quietly pretend this never happened, right? So timeline, move back over here. We just wrote that one function, or a colleague comes to us and says, can I ask you a favor? I need one more function from you. Hey, what do you want? Well, I want to not only total the values, I want to total even values. You say, are you serious? Do you want something like this? Yeah, that's exactly what I want. Well, no, don't implement it. Instead, what you do is you do a little bit of refactoring now that you know this is what your colleague wants. And the little refactoring is, you're going to say util.function dot, and I'm going to call predicate, which is yet another functional interface. And I'm going to go back to this code. Now this code is going to take an extra parameter called predicate integer, and I'm going to call it selector here for a minute. So now our values went from a regular method to a higher order function. It not only takes an object, it also takes a functional interface. So in Java, a higher order function normally takes a functional interface as a parameter. That's a way to know whether it's a higher order function or not. Well, now that we have a selector, I'm going to say if selector dot test the element. If the selector is happy with the value, total it, otherwise ignore it. Now I can come back and refactor this code, and I can simply say element, and I can say true, and you can see that it's totaling all the values. However, let's do something a little different here. I'm going to say public static boolean. We'll call this as, let's call this as is even, where I pass a number to this, and I'm going to simply return in this case. Well, let's simply say the number over here, mod 2, so right, there's the number mod 2 is equal to 0. Now I can come back to this code, I can do something a little different. I can say output total values, and I'll say values comma, given an element is even, and I can pass the element to it. So now if you notice, you can see that we are reusing the function we had a minute ago, but we are able to reuse it over here. Likewise, what we could do is if your colleague comes to you in a few minutes and says, I need another function to find out if the total the values which are odd, you tell your colleague, well, go back to your desk and do it yourself, because I've refactored the code in a way you can actually reuse it. So now you can see is odd, and we can of course call the is odd function very easily and get the results over here. However, let's come back to Java again for a minute. Java does something a little bit more interesting. If you look at this code for a second, just stare at this part for a minute, what do you have in here? Well, obviously it's a Lambda expression, that's great. But what does this Lambda expression really do? It receives a parameter, okay, that's great. And what did it do with the parameter? It simply passes that to this other function. Well, if you're into design patterns, I got a name for this design pattern also. I call this the office space pattern. Remember watching the movie Office Space? Tom, what do you do here? I take the requirements from the programmers, from the business people, and I give it to the programmers, right? Well, that's what this Lambda does. It doesn't do anything useful. It simply takes this parameter and turns around and says, here, you take it, right? Absolutely nothing intelligent. But if you start writing this code, about the 7th time you're going to get very angry writing this code. You're going to say, that's stupid. Why am I writing a Lambda expression when I'm not doing anything interesting? But history has shown us one thing very clearly. Java programmers never write stupid code. They invent IDEs to vomit stupid code, right? So they knew this was coming, right? And the next thing you will do is you'll be tweeting to each other, hey, what's the stupid IDE shortcut you're using to generate this call? Well, they knew this was coming. So they created what's called a method reference. Simply you pass the name of the method and it takes care of the rest for you. So you don't have to be really sitting there and writing that low-level code. And those are called method references. So you can start using method references very easily and simply put this knows that you are receiving a parameter and you are simply passing the parameter. But it's pretty smart though. It knows whether to take that parameter and use it as an argument, or to take that parameter and use it as a target for a method call, or a combination of that. It can intelligently figure that out for you. So that's an example of creating a higher order function. But this takes us to one other level as well. Now that we passed a higher order function here, lambda to this particular function, we can refactor this code also to make it more functional in style. So we could simply say return, and in this case we're going to say numbers.stream. But what are we interested in doing here? Well, we're not interested in totaling all the values. We are only interested in totaling a select set of values. So the function for that is called the filter function. So we're going to say filter using the selector, and then we could say over here reduce, and for a value of 0 to be the initial value, we can say go ahead and perform a sum operation on the values. So that turns into a functional style of code as well, rather than being low-level imperative style. We saw map earlier, and we said a map is really a transformation function. A filter is more like a coin sorter, so you pass the values through it. Some small values can fall in, and bigger values kind of roll over. So this filter is different from map in a couple of different ways. When it comes to a map, the number of output is exactly the same as the number of input. No questions asked, right? So the map will give you the same cardinality. However, the type is a different story. You could get a list of names as an input, and you can transform it to their addresses, for example. Or you could get a list of addresses, and you could transform it to zip codes, for example, whatever that could be. So the output and input types don't have to be same in the case of a map, but the cardinality is the same. Filter, on the other hand, is completely opposite. In the case of filter, the output is a subset of the input. There's not just a different same type, it is the subset of the objects. But you could get 0 objects. That's a perfect filter, right? It blocks everything, you cannot see through it. Or it could be a big hole and everything goes through. So you could have a filter which is blocking everything. You get a 0 output, an empty collection. Or you could get a few values like evens and odds and whatever you want to do. And then you can say, give me everything like a true. So you could have a different kind of filter. So we talked about map and filter. Reduce, of course, is the last operation in here that we are seeing. And a reduce is a transformation that is very different from map and filter. A map and filter always work with one element at a time, whereas a reduce is very cross-cutting. So a reduce says, I'm going to take this value and do something with the next one, take the result of it, work with the next one, take the result of it and work with the next one, and take the result and work with the next one. Sometimes this is called a fold left or a fold right, depending on the direction you go through. So languages differ in what they call this. In Scala they call it fold left and fold right, and there's also a reduce which doesn't take any initial parameters. In the case of Groovy they call it an inject method, or whatever the names are, but essentially these are the reduce operation which is cross-cutting. So if you want to work with every single object individually, you normally use a map or a filter, but if you want to go cross-cutting and derive a collective response, you would normally work with the reduce operation. So that gives us an idea about how to create with higher order functions. But what about function composition? Yes, please.
Now it's getting about time to take a break.
You want? Absolutely, we can take a break. 10 minutes break?
Yeah, don't need more than that.
Excellent.